Hey guys, today we are going to be getting into our second video for topic number 4. Again, stoichiometry. This time specifically we'll talk about molar mass and mole ratios. So one thing that we are going to need to know is about our AMUs, atomic mass units. We've talked before about the subatomic particles. We're talking here about our protons, our neutrons, and then electrons. We talk about the differences between these things, the mass differences. For example, again, protons. The proton has a relative mass of 1, and the neutron has a relative mass of 1. The electron has a relative mass that's so small that we say that it's negligible. It is 0. Okay. So what we need to be aware of is that the actual masses have a specific gram value, but we're using relative masses here. Okay, we call these atomic mass units, relative masses. And it just makes it easier when using this notation for us to consider the mass having a direct correlation to the number of particles that are in there. Now, the definition we're going to give to AMU is that 1 AMU is 1.66 times 10 to the negative 24th grams. Okay. The idea here is, again, atoms are really small. By putting these in atomic mass units, what we've done is we've put them in a scale that's just easier for us to understand and communicate our thoughts. So here's an example of this. Okay, we have one atom of our chlorine 35 isotope, and it contains 17 protons and 18 neutrons. So we have a total of 35 atomic mass units, since, again, electrons we don't consider. So we would have here 5.81 times 10 to the negative 23 grams. This is the actual mass. Okay, so whereas the relative mass that was given is the 18 and 17 neutrons makes 35 atomic mass units, we're saying that 35 atomic mass units is equal to 5.81 times 10 to the negative 23rd grams. So the idea there is if we were to take, now just to relate these things, if we said that we had our 30, oh wait, actually there's one more thing that I forgot to mention here. Let me go back. Before I get into the way these things relate to each other, what I want to do is I want to talk about Avogadro's number. Okay, so we have this is such a small scale, right? 10 to the negative 23rd grams. What we do is we have a new unit that we're going to talk about in a little bit here called the mole. The mole allows us to put in a relative number of particles. So we say that 1 mole is 6.022 times 10 to the 23rd particles, and this number of particles multiplied by the number of grams in these atomic mass units that are given, right, should give us a set number of grams equal to the AMU. Okay, so let me write that in here. What I'm saying is, for this specific chlorine 35, it has an actual mass of 5.81. 5.81 times 10 to the negative 23rd grams. We take this actual mass in grams, right? This is equivalent to my 35 AMUs. This actual mass can then be multiplied by the number of particles per mole. Okay, so 6.022 times 10 raised to the 23rd power. In multiplying these two things together, I find the actual number of grams in 1 mole. So the grams in 1 mole, this many particles, is equal to 35.0 grams. Okay, so we'll talk more about this, but hopefully that made some sense. Now we're going to talk about the molar mass, specifically the relative atomic mass, this RAM, relative atomic mass of a single atom. So we say that this relative atomic mass is the weighted average, and you recall that we learned to calculate these earlier. It is the weighted average of all the masses of all the atoms in a normal isotopic sample of the element. So a standard sample, right? The standard sample is going to have multiple isotopes in it. Then what we do is we say that this molar mass is based on a scale that is based upon carbon-12, this carbon-12 isotope. We say that 1 mole of anything is equal to the same number that 12 grams of carbon-12, the carbon-12 isotope, has in it. So 1 mole of whatever the thing is, right? 1 mole of particles is equal to the same number of particles that are found in 12 grams of carbon-12. Okay, so it's the number of particles found here, the number of particles found there is equal to 1 mole of those particles of anything. Okay, so what we have talked about before is that we have multiple isotopes. Okay, every element that we have is based upon several different isotopes that have different specific masses. Then what we do is we can take the abundance. Remember this word, the relative abundance. 75% is going to be the chlorine-35 isotope. 25% in nature would be the chlorine-37 isotope. Using these percent abundances, we can determine an average value, the average atomic mass. So just for argument's sake, to remind you of how this works, it's going to be that 35 times 75, 35 times 75 plus 25 times 75. Okay, I know I have these reversed, but basically you've got percentages multiplied by mass, percentage multiplied by mass, and then you take that whole thing and divide it by 100, and that gives you the average atomic mass of 35.5 grams, the relative atomic mass, or the molar mass. So when you look on a periodic table, what you're actually seeing is this relative mass. You need to be aware this average atomic mass is what you see on the periodic table. Now, what we do with these, again, we look at these numbers and we can determine the relative mass of either a specific kind of element, right? So atoms, the mass of a number of atoms of an element, or we could find the mass of a specific molecule by, we say, simple summation. Really, it's just adding. If I had the molecule H2O, for example, that H2O is going to be the relative atomic masses of hydrogen and oxygen, right? Simple summation, just add these things together. So again, you add these atomic masses together, and then you can determine the molar mass of a compound, whether that's molecular, if it's a molecular compound, or it would be called a formula unit if it's an ionic compound. So let's go ahead and give this some terminology. We're giving these things names now. So molar mass of an element, okay, a specific element, the molar mass is called relative atomic mass. If we're talking about a molecule, okay, so elements, that would be like the element copper, Cu. If I have a compound, for example, water, H2O, right, it's a molecular compound because it has two nonmetals together. We would call, for molecules, this is known as the relative molecular mass. And then finally, when we're dealing with ionic compounds, such as salt, NaCl, then the sum of the atomic masses of sodium and chlorine here, so again, an ionic compound, the sum that we find is referred to as the relative formula mass, RFM. Okay, so just some terms that we should be familiar with. When we talk about molar mass, we're not usually overly specific about which molar mass, whether it's molecular, formula mass, or relative atomic. It's in either case you're talking about molar mass. So now let's get more in depth on Avogadro's number and the mole idea. So we always like to talk about our substances being measured in moles as opposed to grams, because grams are a compared unit where we want a counted number of things. Okay, so the mole is, again, it's a standard counted. Make sure that you understand that this is a counted number of things. Okay, it's a counted number of particles, whether those particles are atoms, ions, or molecules. The mole, again, the mole is the amount of any substance that would equal the number of particles in a 12-gram sample of carbon-12. So this was our definition from before, and just to restate it, make sure that we understand this. In 12 grams, there's a certain exact number of particles. Okay, in 12 grams of carbon-12, that number of particles is what we call a mole of those particles. So Avogadro's number specifically, we give it a value. The constant, or Avogadro's number, would be called, has the value of 6.022 times 10 to the 23rd particles per mole. This many particles per mole, right? So it has the unit per mole. Okay. So when we use this, what we can see here is we get some relationships. We have, if I had 1 mole. A mole isn't actually anything on its own, okay? Like, a mole just means the number. It's a mole of the thing. So 1 mole of copper atoms is equal to the number 6.022 times 10 to the 23rd of copper atoms. Okay, so you have to have that idea in mind, that a mole, the word mole is just a number. It's just like the word dozen. Dozen has a meaning. 1 dozen, let's say the thing is roses. 1 dozen roses is always equal to 12 roses. So again, we have this word dozen. 1 of this word dozen is equal to the value 12. So if I had, for example, 3 dozen, we'll switch it up. We'll say 3 dozen eggs this time. Okay, so it's a new thing. 3 dozen eggs, we would know that that means there are 3 12s, 3 dozen. That would be 36 eggs. Okay, so the same logic applies here. If you have 2 moles, it's 2 times 6.02 times, or 6.022 times 10 to the 23rd. Now let's get into to using this. First off, let's list the relationships that we do know now. So these are the mass-mole relationships that deal with relative atomic mass. First, moles of an element. The moles of an element is equal to the mass of that sample divided by the atomic mass. Okay, and that would also be equivalent to, again, mass of the sample over molar mass is the general term for this RAM value. When we're dealing with not elements, okay, so the element idea, that's like, again, like copper. When we're dealing with molecules, for example, again, let's say CH4 this time, that's a methane molecule. For molecules, we're using the relative molecular mass, but we can also just say that the number of moles would be the mass of the sample divided by its molar mass. And finally, for ionic compounds, okay, so let's say we have potassium fluoride. This time around, it is, again, mass divided by, yay, there's always a little typo. This is not the random atomic mass, this is the relative formula mass we talked about. Okay, formula units. Ionic compounds have formula units. So mass of the sample divided by the molar mass given here. So we can use this molar mass as a conversion factor. We can convert between moles of a substance and grams of a substance. So if we're given the substance CO2, we want to convert from 23.95 grams into moles. So again, what we have here, 23.95 grams CO2. This is the shorthand notation, 23.95 grams CO2. What we're going to have to do is look up the molar mass based on the relative atomic masses. So if you look at these atoms, we've got carbon and oxygen. So we have 1 carbon and we have 2 oxygens here. That's going to give us a mass. From carbon it's 12. From oxygen it's going to be 16 times 2, which is 32. Add the two together and we find there are 44 grams of carbon dioxide in 1 mole of carbon dioxide. There we go. So to solve this, what we're going to do is just, again, using dimensional analysis, 23.95 grams of carbon dioxide. We're going to cancel grams of carbon dioxide and find moles of carbon dioxide. So our coefficients here, remember it's 44 grams to 1 mole. 1 mole, 44 grams. Okay. So when we do the math there, what we would find is multiply top times top, divide by the bottom. You'd find we have 0.5443, and then the unit carries over. These are moles of carbon dioxide, CO2. So another example going the other way, now we want to take moles, 0.496 moles of CO2, and convert that into grams. So we will start just like before, 0.496. This time we have moles, so we're going to abbreviate that MOL of CO2. We do our dimensional analysis. I love, yeah, it's doing a random dot thing on me. Well, okay, cool. Yay, technology. So we have these 0.496 moles of carbon dioxide. What we're going to do is we want to cancel these moles of carbon dioxide. So cancel moles CO2 on bottom, and we're going to have grams of CO2 on top. Okay, moles on bottom, grams on top. It works right to left for some reason. Okay, using that same conversion factor that we determined here with our molar mass, right? There are 44 grams per 1 mole. We're going to write our 44 gram up on top and our 1 mole on bottom. When we calculate these, we're going to see we have 21.8, carry the unit over, grams of carbon dioxide. So hopefully this idea is making some sense for you. Now I'll let you practice task 4D on your own. You're going to go ahead and plug these answers in online and check to make sure you're getting it. Be aware for number 5 here, we're asking how many particles are present. Particles are present, so you're going to have to be reminded of this 6.022 times 10 to the 23rd, 6.02 times 10 to the 23rd particles per 1 mole. Okay, so don't forget that relationship. Okay? Now let's get into mole ratios. So first off, if you know the number of moles of a substance that are in a chemical reaction, okay, if you know how many moles are given, and you know the balanced equation, you're going to have to know a balanced equation, okay, because what this lets you do is it lets you put together a ratio of moles of one thing to moles of another thing, okay. What we can do with that information is we can essentially convert from one substance to another within a reaction, determined based on having some quantity of reactant, okay. So let's say I start with 50 grams of reactant. I can figure out how many grams of product would form, okay. So the idea there is we have a relationship between these two species, and going through moles, the counted number of particles, we can convert. So the name that we give to this is, we call this the mole ratio, okay. The mole ratio, and it really is literally just the coefficients of the two substances that you have in the reaction. So to give you one example, if you had water, no, not water, let's say peroxide, H2O2. So hydrogen peroxide, H2O2, this can break down into water, H2O, and oxygen gas, okay, so O2. So in balancing this one out, we're going to say 2 and 2. We now have our coefficients that work for all of these. So if I started with 50 grams of peroxide, this reactant, I would be able to convert using this relationship of 2 moles of H2O2 to make, in this case, let's say 1 mole of oxygen, 1 mole of O2. Or I could take the 2 moles of peroxide and find out how many moles of water. Notice that when these are the same, the number of moles I start with will be the same as the number of moles I end with for that specific species. Now, in order to convert substances, the first thing that we're always going to have to do is begin with a correct balanced equation. If the equation isn't balanced, then the mole ratios won't be right. So you have to check that first. say that we're given this example, nitrogen gas and hydrogen gas combine to form ammonia gas. So before we even get into the actual nitty-gritty of the problem, we want to write this out in the correct balanced form. So nitrogen gas would be N2 and hydrogen gas would be H2. These combine and they're going to form ammonia. Ammonia is NH3. Now these are written all as gases. However, for stoichiometry, their state isn't going to be relevant to us. So for right now, I'm going to leave that out. Later on, it's going to be very important, but that's going to be on later in the course. But for right now, we look at this and we see that it's not currently balanced. So we need to do our balancing. My nitrogen is 2. My hydrogen here is 2. And then my nitrogen and hydrogen shown here, I've got 1 and I've got 3. So to make this work, first I'm going to fix my nitrogens by adding a coefficient of 2. That changes this to 2, this to 6, and then I can add a coefficient of 3, and that balances us out. Now our second step to convert between substances is we're going to bring back that molar mass concept. You're going to find the number of moles, how many moles are present in the substance that you specifically start with, the thing that you have, using the molar mass of the substance that you have. So here is that balanced equation that we just wrote out. And in reading the question, we had 65.75 grams of nitrogen gas. Okay, in fact, I'll jump back there and show you. Again, this says calculate the mass of hydrogen. So the mass of hydrogen means my need. If we break this down, we analyze for the have and need. I need grams of hydrogen gas. How many grams, what is the mass that would completely react with 65.75 grams of nitrogen gas? So that means, again, the given or the have would be my 65.75 grams of N2 gas. Okay, so let's jump back forward here. So again, this is the information that's given to us. What we'll have to do is if we want to convert from grams, right, we want to get from grams into moles, we're going to have to use molar mass for this conversion. So we looked at the periodic table for this substance. We see that nitrogen, a single nitrogen is 14. But in this compound there are 2. So to find the relative molecular mass, we're going to go 14 times 2 gives us 28 grams per 1 mole for nitrogen gas. So take this N2, we can now go ahead and cancel grams of nitrogen on the bottom and find moles of nitrogen up on top. So it's 1 mole of nitrogen for every 28 grams of nitrogen. When I go ahead and plug this into my calculator, you're going to get 65.75 times 1 divided by 28, and we find that this equals 2.348. Carry the unit over, it is moles of nitrogen gas, N2. So now, the third step is we have to convert between substances. So now we're converting from moles of the given into moles of the unknown. Okay, so moles of what you have into moles of what you need. That's our conversion. In order to do this, we have to use that mole ratio that we determined. Okay, so in looking at our chemical equation, we can see that our have substance, the thing that we begin with, what we have, was the nitrogen gas. The thing that we need is the hydrogen gas. So look at the 2 coefficients. It's not shown, but this is a 1. So this means that my mole ratio is 1 mole of nitrogen gas for every 3 moles of hydrogen gas. Okay, 1 mole of N2 is equal to 3 moles of H2. So if I begin with my previous answer, 2.348 moles of nitrogen gas, what I can now do is I can cancel moles of nitrogen gas. Okay, just let this unit guide you. Cancel moles of nitrogen and determine the number of moles of hydrogen gas. Looking at the coefficients, based on this conversion factor, the mole ratio, I see 3 moles of H2 for every 1 mole of N2. When I calculate that, Take the top, multiply the top, divide by the bottom. We get that it is 7.044. Carry the unit over, it is moles of hydrogen gas. Now the last thing that we're going to do, now that we have gone full circle, we started with grams, I'm going to say grams of substance A. We went into moles of substance A. Then we went into moles of the unknown. I'll say that's moles of substance B. We now have to go back into grams of substance B. So this is going to require that we use molar mass for the unknown substance. So molar mass of substance B. What we have, again, the results of that last step are 7.044 moles of hydrogen gas. What we're going to do is see that, again, it's hydrogen. If you look on the periodic table, hydrogen has a relative atomic mass of 1. Since the molecule has 2 hydrogens, we take that mass of 1, multiply by 2, and we get that there are 2 grams of hydrogen gas for every 1 mole of hydrogen gas. So when we set up our conversion now, again, let the units guide us, it's going to be moles of hydrogen compared to moles of, yes, I don't want moles anymore, sorry. I want grams. I want grams of hydrogen now. So we're not dealing with a mole ratio. What we're dealing with now, again, is molar mass. So plug in the values we had here, 2 grams of hydrogen for every 1 mole of hydrogen. Essentially, we're taking 7.044 times 2, divide by 1. And what we're going to get from that is 14.09, carry the unit over, grams of hydrogen gas. So 14.09 grams of hydrogen gas would be formed from that initial number of grams, the 65.75. So your next task is look at this reaction, calculate the mass of oxygen required to produce 2.23 grams of carbon dioxide, and then your second task is find the mass of water. So you're going to have 2 different stoichiometry problems. I'll let you work these out online. Hopefully it all makes sense. Throw questions up on Facebook or send me an email.